I'd like to welcome Dr. Abe Holland, who joined IDA in 2019 after completing his PhD in public policy at Harvard University. At IDA, Dr. Holland is an applied microeconomist that has led a range of analyses across defense manpower, operations, and infrastructure topics. He's also a founding member of IDA's Climate and Energy Security Working Group, whose research focuses on supporting IDA's capability to bring the best available climate science to today's national security challenges. In addition to being a U.S. Air Force veteran, he received his undergraduate degree from Dartmouth College and graduated summa cum laude in economics and Chinese literature. So, come on up.
I had no idea you were going to read that. All right. So thank you. And before I begin, I want to also just highlight. Well, my name is on the slide. I'm deeply indebted, I should say, to my research assistant Astrid Birch, and our technical reviewer was another researcher at IDA, who's the former Black Hawk pilot, who in the UH-60 Black Hawk will play an important role in this presentation, and having somebody who actually has flown these things is an important part of our quality process. So for those two, thank you again for all your work in making this presentation come together. This work is actually a public version of work that we've done for sponsored work that uses sort of actual data that is being currently used for aircraft and other types of things within the military. Everything I'm going to present today is public. And as an economist, rather than as an aerospace engineer or a climate scientist, my role within this work is really about figuring out how to stitch all these different pieces together. And in fact, this is one of the key challenges when dealing with climate change, and as in general, is it's such a massive topic. It affects so many different types of systems. Figuring out how to get all these different communities to talk together and work together is actually, I think, probably the key challenge for researchers in the space. So with that, we'll be talking today about projecting regional climate change effects on aircraft performance. And just as a start, one of the things that was important when we were kicking off our work is that we didn't want this to be a new climate science project, right? We as in the Institute for Defense Analysis, our job isn't necessarily to innovate brand new climate science. Our job is to figure out, okay, how do we take the best of available science and take our understanding of the defense context and merge these things? How do we bring sort of all the best of this combined understanding together and answer this important national security question? And so with that, we sort of started our process by just sort of understanding what's already publicly available in many of these different spaces, and then how do we bring them in? And one of the things that I'm going to be talking about today, or actually the main thing I'm going to be talking about today, is based on this McRae et al. Paper from 2021 around assessing aircraft performance in a warming climate. And so I'm going to be using a slightly different data source in a slightly different context, but the sort of original motivation for this kind of analysis came from McRae. And so for that, thank you very much. One of the things that I'm going to be talking about today, and I can't actually see the top of the slide. Okay. For this analysis is that we're going to be using the UH-60L. This is the Black Hawk. There's a Navy and an Army version of this. We're going to be using the Army version. And one of the things that's important to think about when you're thinking about this kind of aircraft is that there's a wide range of environmental factors that influence the performance of a helicopter, right? Everything from like its power margin, its maximum gross weight, and low capacity, which is going to be our focus for today, hover ceiling, max range, fuel consumption, a bunch of other factors. That's just the gross performance characteristics. An important thing, and one thing that's actually sort of not been done in the literature, I think is important, is the interaction between these external environmental characteristics and how climate change might affect it, and then the interaction between that and all these other system subcomponents. Maybe this is the kind of thing that your kind of network analysis might be useful for in terms of understanding maybe there's different heat tolerances, for example, for different types of subsystems within an aircraft. Being able to understand how sort of gross environmental characteristics how those changes might influence the effectiveness of those different subsystems and what it might mean for aggregate aircraft performance is certainly an area that's worth further exploration. But for today, I'm only going to be focusing on this first order. I'm going to be talking about the changes in load capacity for a UH-60L between now, our historical reference period, and a projected future climate in 2050. So what we're going to be doing is we're taking the sort of for a publicly available version of the Navy's operating guidance for the UH-60L. This is not just guidance. This is actually the rules for how to safely operate an aircraft. Right. We're going to take the sort of the instructions that pilots have for how to change, for example, the load capacity of the aircraft based on local environmental conditions from that manual. We're going to move to this particular region of interest, which we're going to be using sort of the North Luzon or Luzon region of the Philippines. And then we're going to be using a series of climate projections from the Community Earth System Model 2, which is a suite or a large ensemble of climate models that are sort of and we're going to be focusing on sort of a period of sort of between 2040 and 2060, which we're going to then call 2050. Right. So we have this this period of time that we're interested in looking at in terms of, okay, how might aircraft performance change relative to like a historical reference period versus say this North Luzon region in 2050. So one of the things that's actually sort of really useful for us when thinking about this. So what do we do? Well, on the left-hand side here, this figure, what you're looking at is this is climate model data, and what we've done is we said, okay, in this region, what is the maximum load capacity observed from say 1980 all the way out to the end of our run, which we're going to be using. Well, 2060 is where I want you to end. And then what is the minimum max load capacity, the mini-max, right? So the least you could carry and then the most you could carry within a given year. And that's these two lines. And what you should observe, or what I observe first, is that the sort of the regular gap that you observe between these 2 points, that's just your annual seasonal variation, right? It's just that for this region, the most you can carry versus the least you can carry, it's about 1,300 pounds, right? And then the slopes of these two lines is what we would describe as the climate change effect, right? So this is over time, sort of systemically, what is the projected consequences of climate change for the UH-60L in terms of load capacity if you're operating in Luzon? And that's actually quite small, right? In this figure on this first figure, it's about 5 pounds. Doesn't seem like it's a whole lot, right? And we're only looking at the annual max and the annual max. Now, I think that this brings up an important point, which is, well, this sounds like a nothing burger, right? Why should we care about climate change in Luzon for if we're operating a Blackhawk if we're only talking about 5 pounds between now and 2050, right? In fact, when you take that same data and we look at it slightly differently, we're now looking at this next figure over here, we potentially end up with a very different story. And this is something that if you're an operational commander on the ground, this is a kind of, we think that this is sort of a more useful way to look at this information. So what we have here in this bar chart is our historical reference period, which is from 1979 to 2014, and our projected future, which I'm calling 2050, but it's really sort of this period from 2040 to 2060. And in this first part, what we're saying is, what share of days in a year might you expect to have at least a 100-pound load capacity reduction for a UH-60L operating in Luzon? And based on the historical period, what we're saying is actually about 60% of the time you should expect to have to reduce your load capacity by about 100 pounds. Okay, now let's fast forward to 2050. What do we see? Well, actually now it's almost 80% of the time you're going to have to reduce your load capacity by at least 100 pounds. Okay. Now, what about 200 pounds? Oh, it's about the same, right? We're talking something around 45% of the time. You have at least a 200-pound load capacity reduction. What about 350 pounds? Well, in some cases, in fact, it looks like what's happening is that, the historical reference period, it's about 10% of the time, roughly, you have a load capacity reduction of at least 350 pounds. Okay. But when we start looking at the projected future, we say, oh, actually, 20% of days, you end up with a load capacity reduction of at least 50 pounds. This is actually something that if you talk to an operational commander, they'd actually might care about. Why? Because if you take like the weight of a combat loaded soldier, right? It's around 350 pounds or 250 pounds, right? Depending on who you talk to, it's 250 pounds or 300 pounds. So in fact, what we're talking about now is we're talking about taking soldiers off airframe, right? And if you're a commander who's trying to complete a mission, we're talking about, yes, in fact, you are seeing this sort of potentially meaningful increase in the number of days in which you have to actually reduce the number of soldiers you can take into an operation as a result of climate change. Now, again, this is the same data, both figures, just presented differently. So I think the second thing I would like to emphasize when you sort of look at this is that when you're talking about different types of climate change analyses, one of the things that's actually quite challenging, I think, is really thinking concretely about what is it that your decision maker that's going to be consuming your analysis, what is the thing that actually matters to them? Is it the thing on the left or the thing on the right? All right, so what I've done is I've shown you, well, I've shown you this particular analysis, but I've also shown this is really a demonstration in the sense that there's actually a wide range of potential metrics that we might use with the same kind of basic analytical approach. Whether we're thinking about, well, how might climate change influence the range? Maybe it's the required torque, hovering out of ground effect, or otherwise carrying external loads. And just this kind of sort of simple example. There's other ways that we might also use this kind of approach, which is in sort of a more vignette-oriented approach, where we're trying to say, well, actually, let's take a very specific mission and then sort of understand, could we complete that specific mission? And this is, an example might be something like, okay, we need to use this aircraft to carry an external load for 5,000 pounds for 150 nautical miles to a landing zone that's at some kind of higher altitude. Can we do that or not, right? And use that as sort of our way of understanding the impact of climate change. So that's, in fact, everything. I've zoomed through it pretty quickly. I'm happy to take questions.
Hi, this might be a basic question, but what about climate change is causing these effects in the aircraft? Is it just the temperature or humidity, or what is doing this?
Ooh, good question. Let's see, I might have. It's a number of different things, right? Right, temperature, humidity, pressure, altitude, and temperature really is sort of the key things here for this particular example. But it's really just physics, right? And it's actually sort of the nice thing about this, right? It's like with these kinds of analyses, is that once you've sort of figured out sort of how to sort of put these different pieces together, almost any airframe, right? Any airframe is subject to the same fundamental physics. You can then start to say, oh, well, how might this trend influence this particular type of aircraft or this other type of aircraft? It's very flexible in that sense. The other thing that's sort of interesting about this is that this figure on the left, this is what's actually in these manuals, right? And so imagine being an aircraft operator sitting in your cockpit and you're trying to figure out, okay, how does this, what are the conditions like, and then how do I do this? So what ends up happening is that these things are developed with sort of rules of thumb and based on experience, right? I could imagine sort of another type of analysis would actually take a much harder look at sort of the underlying physics behind how these changes in local conditions influence aircraft performance, and then create tools that would support operators in making more precise predictions about load capacity. I actually think that would be a great analysis and a great resource for operators. I think that's actually important in many contexts also, because when you have these kind of chunky decision rules, you can end up with sort of like two things happening, right? One is that you could have sort of movement that's all inframargin, in the sense that like there's some actual change in performance, but your decision rule doesn't reflect that, so you don't change anything, and you can end up with problems, right? And in the extreme case, you could be talking about, well, maybe there's aircraft that are falling out of the sky, right? In sort of the other end, though, is that if you're already at the margin of one of these decision points, and you end up with a relatively small change in the environment, and it pushes you over that threshold, you're now restricting like your aircraft performance characteristics far too much relative to what's actually necessary. and that could have operational implications. Yeah. Other questions?
So to the extent that it is temperature that's impacting some of these changes, would it be accurate to say that the hottest days aren't getting much hotter, but there are more hot days than there used to be in Luzon? Given that the proportion of days where there's a restriction has gone up, but the max is not changing very much?
So I actually have some slides which I didn't include for Luzon, but it's actually two things happening with climate change that are important to keep in mind. So yes, there is a mean shift, right? And so in the example I showed you for 2050, I was using a scenario that's sort of like the average scenario. But actually at 2050, it doesn't really matter what scenario you pick; they're all basically the same, right? So you see a mean shift, maybe we're talking about 1 degree Celsius or something like that. You end up with a mean shift, but you also end up with a spreading of the distribution, right? And so we talk about sort of more extreme events, and so both things are happening at the same time, and that's actually what you're seeing in some of the data, right? Is like why you end up with this increase in the number of days where you have a low capacity reduction of sort of more than 350 pounds. Is that the distribution is widening and shifting at the same time. There was another question in the back. I actually don't know.
I think maybe you just answered it, but the graph on the uninteresting graph on the left, just flat lines to my eye.
Yeah.
I mean, I can't even see an increase, but you're telling me it's there.
No. So in fact, so it should be uninteresting to you, right?
It is.
There is actually a projected, I think, 5-pound decrease, right, in maximum low capacity in this figure on the left. It's so small you can't even see it. It's like orders of magnitude smaller than what you see in terms of seasonal variation.
So the real point is that the average isn't what matters. What matters is you're getting a lot more really hot days.
You're getting more variation, right?
Yeah.
And that if you look at the figure on the left and you're a decision maker, right, you actually miss the point.
Right.
Yeah. So for us, this figure was actually really powerful in terms of trying to explain to our sponsors about sort of how you frame the question really matters, right? And so if we're just talking about maximum low capacity, and you say, well, how much really am I losing in maximum low capacity, and that's the kind of analysis you end up with, you miss
Right.
really what's really important about the kind of risk that they're taking on, or the risk that's being projected by climate change. And that's where we started looking at this figure and trying to sort of display the data in this way, because then we can say, oh, actually, like, you tell me, do you care about a 20% increase in times when you have to, or something like a 15% increase in the times when you have to actually take, service members off airframe that you're trying to use for an operation?
Right. Well, another way of saying it is that averages are almost always uninteresting.
Yeah, my old statistics professor, would say, it's like on average you may be comfortable, but your head is in the oven and your feet are in the freezer, right? Yeah. Any other questions?
All right, let's thank both of our speakers again.